Okay, yeah, so let's go back to where we were. Okay, so what we decided, yeah. Yeah, it's okay, right? Yeah. Okay, so where we were last time was we were going to solve Einstein's equations, and we were looking for approximate solutions. Okay, so the first thing is before you get an approximate solution, you need at least one exact solution. So the exact solution we found was in the presence of a vacuum, that is when the stress energy tensor is 0. And we solved on a particular manifold. That manifold was R4. Okay. In general, when you're solving Einstein's equations, okay, the equations are local, right? This is a differential equation at each point in space-time. So if you're solving on a manifold, you can solve in any coordinate patch. The patch doesn't necessarily have to cover the whole manifold. What you have to do then is you have to know the boundary conditions on this patch. Okay. And for example, if I have another overlapping patch, then I would know the solution here, and I need to specify the boundary conditions on this patch. Okay. And if I have a bunch of patches that together cover the whole manifold, then I can stitch together these solutions, okay, in different patches by matching them in the overlap regions. Okay. And because we know how to transform coordinates between one patch and another in the overlap regions. All right. In this case, it's simple because R4 is covered by a single coordinate patch, okay, which covers the entire space. But remember that we could be solving this even without looking at the full coordinate space. Okay. The important thing is that we are assuming that we are finding a solution to Einstein's equations in vacuum, where we assume that at large T, X, Y, Z, the solution is Minkowski. So that gives the boundary condition. And then everywhere in the interior of R4, not just at large T, large X, large Y, or large Z, in the interior also, the solution turns out to be the Minkowski metric, okay, which is this one with -1. Okay, so this is the obvious solution, and we showed it's the exact solution last time. And now what we wanted to do is, and we also saw that if you look at the geodesic equation, it gives you exactly particles moving with a velocity v, which is less than c, if you assume that it moves along geodesics, which are time-like, okay, curves which are time-like. In this case, if in the absence of external forces, it moves along a geodesic, and those geodesics are time-like. Okay, and then going further, okay, what we had was now we had an exact solution, and now we're trying to perturb around it. Okay, and this you can do around any exact solution. Okay, so we just looked at the simplest exact solution, which is the Minkowski metric. So when we perturb around the flat Minkowski metric, we get what is called linearized gravity. Okay, or it's gravity about flat space-time. And flat because the Minkowski metric has no curvature. Okay, we computed the Riemann curvature tensor and showed it 0. So now what we're going to do is basically assume that the stress energy tensor is small. So let's say the densities and pressures, if you think of the stress energy tensor as being made up of some kind of ideal fluid, those are small. And so it's proportional. We kept some lambda in here just to remind us that the densities are small. Okay, so we kept the lambda explicit. Okay, so the stress energy tensor we replace by lambda t mu nu. At the end of the calculation, we'll take lambda to 1. Okay, and the smallness is in t mu nu itself. It's not in the lambda. Okay, the smallness is in t mu nu itself. The lambda is just to keep track of where the smallness is. Okay. Okay, and so then we solve for g mu nu. Okay, so we have to solve this equation for the metric. And now the important point is that we know the exact solution in the limit lambda goes to 0. That is the Minkowski metric, assuming the same boundary conditions. Okay, so what we're trying to find now is by perturbing this, we should get a solution which is also has order lambda corrections. Okay, so systematically, order by order in lambda, we should be able to find corrections to this equations of motion. Okay, and that's what we were trying to do. We were trying to work out the first order correction to the metric, okay, for small lambda. Okay, and yeah, where were we? Yeah, and so I said something which might have been a bit mysterious last time, and there was a question after class which helped clarify this. Okay, so we're expanding our metric as eta mu nu plus lambda h mu nu, and I said from now on our convention will be to raise and lower indices using eta rather than g. Okay, strictly speaking, what I mean by that is, so we also worked out the inverse metric, which is eta mu nu minus lambda h mu nu. And we showed to first order, this is exactly the same as taking the inverse of this full matrix. Okay, to first order, the inverse matrix is just this. And so first order in lambda. And now I said that we'll raise and lower indices using this matrix. Okay, so we can raise indices using this metric. Okay, that's the right way to do it. Now, if we raise indices of quantities that are already order lambda, okay, and we're only working to order lambda, then we only need to consider the first part of this, because this multiplying anything which is order lambda will raise it to lambda, will be order lambda square, and we can drop it. So effectively, whenever we are raising and lower indices, we should always be raising with capital G, but our notation will be such that we are always, since we're always raising and lower indices, raising and lower indices of things which are already order lambda, it is good enough to raise them with capital eta or lowercase eta. So when we talk about the raised or lower indices, we're raising and lowering with respect to eta. Okay. All right, then yeah, so we showed explicitly that this was the inverse metric to order lambda. And then here was a really important point, okay, which is that in GR you have coordinate freedom. You're free to choose your coordinates to be whatever you like. So now, how does that coordinate freedom manifest itself in this linearized version of Einstein's equations? The way it manifests itself is that you can make a coordinate transformation. So we assume that we're changing x to some coordinate y, but that coordinate y is a small deviation away by some order by order lambda. And this is, so I write it in terms of my old coordinate x plus some shift, where the shift is an arbitrary function of x. Okay, so the psi alpha are arbitrary functions of x. So this is a small change, and we showed that the full tensor transformation law tells us the transformation law for the metric. Okay, now we work out the perturbative version of this tensor transformation law to figure out what is the change in the first order part of the metric, that is the change in h or h prime. Okay. And what we showed is at the end of it, the dictionary for h prime and h is related by this. So this is our new perturbation, h prime alpha beta y is equal to h alpha beta x minus partial beta psi alpha plus partial alpha psi beta. Okay. Now, if you think about what we did, right, what we're saying is that we can always make a change of coordinates. We're still looking at the same physical perturbation, just in a different set of coordinates. In that different set of coordinates, this h prime alpha beta is your perturbation. Okay, but it's really describing exactly the same physical setup. Okay. Now this change is only valid as long as the change in our coordinates is small. Okay, the change in our coordinates had to be order lambda for this equation to be valid. If we make a large coordinate transformation, then this perturbation will not be valid. Okay, so our coordinate transformation also has to be perturbative. Okay, so if our coordinate transformation is perturbative, then at linear order in the coordinate choice freedom, we have many equivalent perturbations. Each of them is h prime alpha beta is related to the old h alpha beta by this extra shift. And this freedom is called gauge freedom. You have a freedom to choose your coordinates or choose small changes of coordinates. Those small changes of coordinates lead to different forms of the metric or the metric perturbation. Okay, the eta part will always stay eta. The perturbation will change. Okay, but all of those changes in perturbation are really describing the same physical setup. You're not changing the physical setup. You're just changing your coordinates used to describe that setup. Okay. You could, but then your perturbation breaks down. Basically, if what you're doing is a series of coordinate transformations, n, okay, times lambda, and n is becoming large, and therefore your perturbation theory is breaking down, right? So I'm basically, if I repeat this transformation recursively, right, my transformation is really, n times lambda. So yeah, switching from Cartesian to polar coordinates is a large transformation because you are significantly it's not changing in a local neighborhood, right? From t x y z, right, to go to r theta phi t is a big change of coordinates because x is not being perturbed to something small to get r, right? I mean, you're making a very large change from x to r. What we're really thinking of is x plus some lambda times some function of, let's say, t x y z. That is the change that you're making, and this change has to be small. That's how we're imagining that we're getting the new coordinate x prime. Okay, that switching from Cartesian to polar is a large coordinate transformation. Okay, you could have started with eta in the polar coordinates and then talked about small coordinate transformations about the polar coordinates. That's another way to do it, right? But we're sticking with Cartesian, looking at transformations around Cartesian coordinates, small transformations around Cartesian coordinates. Okay, yeah, so this is where we stopped last time. This gauge freedom of linearized gravity. Okay, this is equivalent to the, it's equivalent to first order to the full freedom of coordinate transformations that you can make in general relativity. Okay, so now here's our starting point. Okay, so we assume that we are now working in one of the coordinate systems. It doesn't matter which one, but any one of those coordinate systems in which that perturbation h is small. Okay, that perturbation h is small. So some coordinate system in which you have eta mu nu plus lambda h mu nu as a metric, and that is a good approximation to order lambda. Okay, so in such a coordinate system, okay, so we'll work out first. What do we have to work out? We first have to work out the Christoffel symbols. We want to work out Einstein's equations. We want to work out the left side of Einstein's equations. The left side of Einstein's equation has Einstein tensor. The Einstein tensor depends on the Ricci tensor and the Ricci scalar. The Ricci tensor and the Ricci scalar depend on the Ricci curvature. The Ricci curvature depends on the Christoffel symbol. So first we work out the Christoffel symbols, which we'll do here. Then we'll work out the Riemann tensor. Then we'll work out the Ricci tensor, and then we'll work out the Ricci scalar. Okay. In general, if you're doing anything in a coordinate system, you have to do this complicated mathematics. Okay, this is generally true. We're doing it in the simple case of linearized systems, but you always have to do this. Okay, first work out the Christoffel symbols in a particular coordinate system, then work out the Riemann tensor that has all the information about the curvature, then work out the Ricci tensor, then work out the Ricci scalar, then work out the Einstein tensor. That gives you the left-hand side of Einstein's equations. Okay, in a particular coordinate system. Okay, so the thing is, you might have been impressed by the beauty of Einstein's equation by the fact that it's coordinate free, but to solve the equations, you have to go to some coordinate system, right? For example, it's no good telling me that the laws of physics are rotationally invariant, but then if you're unimpressed by the fact that when we actually solve Newton's equations to find out blocks and pulleys and so on, you have to choose a coordinate system to actually solve something, right? So just because the laws are coordinate system invariant doesn't mean when you solve a particular problem, you don't have to choose a coordinate system. You still have to choose a coordinate system to solve the problem. Okay, but the fact that the laws are coordinate invariant gives you some symmetries of the theory. Okay. 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 So now so we'll work out in this coordinate system where h is small. We'll work out the Christoffel symbol. So this is the formula for the Christoffel symbols. This formula is something that is easy to remember, so you should remember it. Okay, I mean, you'll have the formula sheet, but remember this. Okay, it's not hard to remember. Okay, it's half g mu sigma, so the upper index, and then there's a repeated index which is introduced over here, times. Now I pull out derivatives with respect to this index, and I replace that index by a summed index sigma. Okay, g sigma rho. The next term, I pull out a rho and take a derivative with respect to rho, and then I take g nu sigma. So I replace the rho index by sigma index over here, and the last term is minus. It comes with a minus sign, and it's partial sigma g nu rho. Okay, it's easy to remember that these two are symmetric in nu and rho. Okay, under the exchange of nu and rho. This one is symmetric under the exchange of. This one is also symmetric under the exchange of nu and rho by itself. Okay, and this one appears with the minus sign. All right. Okay, so now we work this out to linear order. Now the derivatives of, so if I take g is eta mu nu plus h mu nu. Okay, and lambda times h mu nu, and the inverse metric g is eta mu nu minus lambda h mu nu. Okay, h mu nu upper. Again, h mu nu upper, it's good enough to think about it as being raised by eta because it's already an order lambda quantity. Okay, it's multiplied by an order lambda quantity. So these raised indices, you can think of them as being raised by an order by an eta matrix rather than a G matrix. Okay. Now, if we look at this, see the derivatives acting on eta will give you 0, obviously, because the eta is a constant. But the derivatives acting on h mu nu will be non-zero in general. Okay. So we'll write out those terms. So we'll just replace G by h. Okay. So over here, and over here. And I also pulled out the lambda because there's a lambda here. Okay. Now this G upper mu sigma has two pieces. It has an eta mu nu minus lambda h mu nu, but I'm already multiplying by something which is order lambda. I pulled out the lambda here. Okay. So since I'm only working to first order in lambda, I just replace this G mu sigma by its leading order piece, which is eta mu. Okay, or eta mu sigma. Okay. So that's it. That's the Christoffel symbol. There's no further simplification for a general perturbation. Now what we need to do is we need to work out the Riemann tensor. Okay. Now here you can either use the form of the Riemann tensor defined in terms of Christoffel symbols, okay, or you can use the form that we had worked out earlier, which we had worked out in the case of a metric connection. Okay, in the case of the unique metric connection, we had worked out this form of the Riemann tensor. The form of the Riemann tensor, it was that formula in Nakahara. Okay, I think it was 7.62, but I don't remember exactly. Okay, you can check it again. It's one of the earlier lectures. So this Riemann tensor is of this form. Okay, and this is with all lower indices. Okay, so it's minus. So the important thing was Nakahara has an overall minus sign missing. Okay, remember that minus sign. Okay, because otherwise you'll get all your conventions wrong. So there's an overall minus sign, minus half partial square g mu rho partial x nu partial x sigma minus partial square g nu rho whatever. Okay, some long expression. The second part involves some gamma square pieces. Okay, gamma, the Christoffel symbols are already order lambda. So gamma square will be order lambda square. We can just drop those. Okay. So the non-trivial part of the Riemann tensor will come only from here. And again, over here, we can just replace g by h. Okay. Because when it's acted on by a derivative, the eta part doesn't matter. Okay. So it's only the h part. So we'll replace g by h everywhere here, and or lambda times h. And what we get is the lambda explicitly here, and then we get these h's. Okay. So it's just the same expression as above, where I've just replaced it by h everywhere here. Okay, so relatively simple since we're working only till order lambda. Okay, now what we have to do is now we want the Ricci tensor. The Ricci tensor is the Riemann tensor, which is R.
Do we actually require the value of the Christoffel symbol in this sort of approach?
Yeah, you do, right? If you had the quadratic pieces, you need them. Right? And even the Riemann tensor itself, we wrote it this way, but this is actually a simplification based on Christoffel symbols. Like you can write it using, partial nu, gamma mu, rho sigma, or something like that. Right? This part can be written using derivatives of Christoffel symbols. So either, I mean, this is just a simplification in case you don't want to use the Christoffels for this part. It just turns out to be simpler to do it this way. Okay, so now we want the Ricci tensor. The Ricci tensor, remember, is in our convention, we contract the first index and the third index of the Riemann tensor. So we multiply by g mu rho. Okay, we multiply this by g mu rho, r mu nu rho sigma, and then we sum over mu and rho. Okay, so sorry, there's no minus lambda by 2 here. Okay, so this is what we want. And again, the Riemann tensor is already order lambda. So the inverse metric, we just have to raise and lower using eta. Okay, we don't need to raise and lower using the full G. Okay, so we have eta mu rho times this Riemann tensor, which we worked out here. Okay, so yeah, so I won't work through the details. Let me just read out the expression. Okay, so R nu sigma, what you get is minus lambda by 2 partial nu partial sigma of h, where h is defined as h alpha alpha. Okay, where h with one index is raised, the other index is lowered, and both are summed over. It's like they're taking the trace of h. Okay, if I think of h as a matrix, okay, it's like taking a trace of eta times h. Okay, sorry, it's eta times h. It's literally this. Okay, which I can regard as trace of, take the matrix eta, multiply by the matrix h, and take the trace. Okay, so this is what this h is. Okay, then there's a box. What is this box? It's just partial alpha. Okay, repeated index summed. So it's just your usual wave operator that you have in Minkowski space. Okay, and this is h nu sigma. And what you have over here is you have some extra term minus partial mu of partial nu h sigma mu. Okay, so this is again, I've raised one index using eta, and here plus partial sigma. This whole thing is acted on by this partial mu. Okay, h nu mu. Okay, so each term you can check has only free indices nu and sigma. Okay, the free indices are nu sigma, nu sigma, nu sigma. Okay, the mu index is contracted here. Okay, and same with this term. The mu index is contracted here, and there's a nu sigma. The other thing is we know the Ricci tensor is symmetric in nu and sigma. So one quick check is This term is symmetric. This term is symmetric because the perturbation also has to be symmetric because the metric is symmetric, right? G mu nu is eta mu nu plus h mu nu. By our assumption, the metric is symmetric. Okay, so this is symmetric. Okay, so this is symmetric, and then these two terms together are symmetric under the exchange of sigma and nu. Okay, so this term becomes this term under the exchange of sigma and nu, and this term becomes this term under the exchange of sigma and nu. So you see that indeed the whole expression for r nu sigma is symmetric in nu and sigma. Okay. Okay, and R, which is the Ricci scalar, is now you contract the indices of the Ricci tensor. So you take G nu sigma, R nu sigma. Again, this is going to be worked out to order lambda. Okay. So again, we'll raise only by eta. Okay, it doesn't make sense to raise by order h. You can ignore those terms. So you get minus lambda by 2. Let's just work this out. So when you contract this, so I'm multiplying this by now eta nu sigma. So what is this going to give me? The first term. It's just the wave operator, right? This is just good old special relativity, right? And it is really special relativity because you're kind of solving in the background of an eta mu nu metric. Okay, so you get box h for the first term. What about for the second term? What happens when eta nu sigma acts on this? Box h, because by definition, eta nu sigma, h nu sigma is h, and I can pull this eta inside the box because it doesn't get acted on by derivatives. Okay, and the last term is this one. Okay, which I'm multiplying by eta eta nu sigma. Okay, so that basically just contracts the nu and the sigma index. So I can write it as nu contracted. Okay, and similarly in this term it's nu and nu contracted. Okay, so what I get is I get twice of this and I get twice of this. So I get overall minus lambda times box h minus partial nu h. Okay, this is the Ricci scalar. So now we have to put together these two pieces. We have to put together the Ricci tensor and the Ricci scalar to construct the Einstein tensor. Okay. So let me just do this and then we'll pause for questions. Okay. So let's take the Ricci tensor, which was this expression. I'm just writing it again down here. Okay, it's just this expression. I've just pulled the minus sign inside. So the first term is minus box h mu nu, then minus partial mu h, and then this term. Okay, this term earlier appeared with the minus sign, but there was an overall minus sign outside. Okay, which I pulled inside. There's an overall minus sign here, which I pulled inside. Okay. And then minus half g mu nu times r, and once again this g mu nu, since r is already first order in lambda, I'll write g mu nu, I'll replace by eta mu nu. Okay, so I get minus lambda by 2 eta mu nu, box h minus partial alpha beta h alpha beta. Okay, this is what we had worked out here. Okay, for the Ricci tensor. Here, see, the thing is, this is a common pitfall, which is why I'll tell you this step. I had written this as partial nu h mu nu. Okay, but when I wrote it here, I wrote it as partial alpha, partial beta, h alpha beta. The reason I changed indices from mu nu to alpha beta is because I already have a mu nu index here. These are dummy indices which are repeated, but you don't want to use the same dummy indices as the indices that are free indices, which are sitting out here. Okay, so you have to be careful with this step, otherwise you'll get completely confused. Okay, so always remember that dummy indices you can always change, but don't use the same letter for a dummy index as you're using for a free index. Okay, because this index is not summed, this index is summed. Okay, and if you remember this one detail, you will avoid many of the pitfalls with index notation. Okay. Okay. All right, so this is the expression for G mu nu. Any questions till this point? Yeah.
The wave operator, how do we actually define del with alpha raised?
Del with alpha raised?
Yeah.
Again, we raise it with eta.
I mean, in this case, it's probably clear because eta is not spatially very important. So, I mean, we raise it from the right side or the left side. I mean, here it does not.
No, because we're always raising with eta, we're not making that distinction. Yeah, it doesn't make sense to raise with eta if you're raising a covariant derivative and a fine connection like this. Okay, then you really have to do what we're really only doing this because strictly this is all valid till leading order. okay, in lambda. Okay, so it's a definition of notation, and what you're saying is, how do I define, let's say this, okay? Do I define this as partial beta or not, right? And does this derivative act on this also? These things you have to, I mean, in such a situation, you have to define what you mean by that, right? Here, we're just making a simple definition because we know how to raise and lower indices with eta, and which is equivalent to raising and lowering to first order in G. Right? Okay. All right. Now we'll make a simplification of this. It's a little cumbersome to work with H because you see that although it's the left-hand side now, you see one thing is it's completely linear in H. Okay, and it involves some wave operators or derivatives acting on H. It's second derivative, linear in H, second order in derivatives. Okay, so it really looks like some kind of wave equation, but it's still a bit cumbersome to work with this form of the wave equation. So we'll make an additional change of variables, okay, just to simplify our life. Okay, so what we're going to do is we're going to define something called h bar mu nu. Okay, we'll use this as our new variable instead of h mu nu, where h bar mu nu is defined to be h mu nu minus half eta mu nu times h. Okay, where h is, as before, it's h alpha alpha, which is eta alpha beta h alpha beta. Okay, so this is what we make this redefinition, and you can show then that h bar, okay, which I defined to be h bar mu mu. So now I raise this h bar index, okay, with eta, okay, which is eta mu nu h bar mu nu, where I've defined h bar mu nu here. This is equal to, okay, I can use the definition of h bar mu nu. So the first term is just h. Okay, when I take eta mu nu times h mu nu, I get h. When I take eta mu nu times the second term, okay, what I have is eta mu rho times half h. Okay, what is eta mu rho times eta mu rho? If you're in 4 dimensions, it's 4. If you're in n dimensions, it's n. Okay, because this is really, if I think about this as matrices, this is the trace of eta times eta, which is the trace of the identity matrix. Okay, so it's the number of dimensions. In 4 dimensions, it happens to be 4. Okay, so this is h minus n by 2 h. Okay, which is 1 minus n by 2 h in 4 dimensions, and in 4 dimensions only, this is equal to minus h. Okay, because n is equal to 4. All right, so h bar is equal to minus h in 4 dimensions. So what that means is I can also invert this equation and write h mu nu in terms of h bar mu nu. And I can write h mu nu as h bar mu nu minus half h bar eta mu nu. Okay, where what I did is I took this to this side, it appears with a plus sign, but then I convert h to h bar, and then it gets back a minus sign. Okay, but this is only true in 4 dimensions because otherwise I would have this would be 1 minus n by 2. Okay. All right, so now what we do is, so we have this expression. So now what we can do is instead of h mu nu, we can just substitute in terms of h bar mu nu and this h bar, which is the trace of h mu nu. Okay, we can substitute it back into g mu nu. Okay, and we can get a wave equation for h bar instead of a wave operator for h bar instead of a wave operator for h. Okay, this leads to a considerable simplification. Okay, so g mu nu in terms of h bar, I won't show all this, but what you get is lambda times minus half box h bar nu, okay, plus half box partial alpha partial mu h bar nu alpha, plus partial nu h bar mu alpha, minus half eta mu nu partial alpha partial beta h bar alpha beta. So the advantage of making the shift from h to h bar is that you don't have these terms involving the trace of h anymore. Okay, you don't have the trace of h bar appearing over here. You don't have just h bar appearing. Okay, which is you don't have this appearing, you just have h bar alpha beta, okay, appearing everywhere. Okay, so that's the advantage of making this shift. All right, you've kind of subtracted off the trace in some sense. Okay, over here. Okay, now remember that we still not use the freedom that we had in choosing our coordinate system, the small changes in our coordinate system that we could have made. We have not used that freedom yet. Okay, so we'll use that freedom now to simplify the wave equation further. Okay, so we remember that this is the general freedom that we had, right? We could always switch coordinates from x mu to x mu plus lambda times psi. Okay, and this leads to a change in the metric or the perturbation h mu nu of this form. Okay, and what we're going to do is we're going to choose our change of coordinates in such a way. Okay, so assume we start with some h mu nu. We'll switch to some other coordinate system in which we have an h prime mu nu. Okay, in such a way that partial mu h in the new coordinate system, that is the primed coordinate system or the y coordinate system, the derivative partial mu acting on h bar mu nu prime is 0. Okay, we'll just choose a coordinate system such that this is true. Okay, so the first question is, can this always be done by a change of coordinate system? Can you always make this choice? Okay, is it possible to make this choice? So what we'll show is by a small coordinate transformation, it is always possible to make this choice. Okay, so this choice is called gauge fixing. Okay? Because now you're getting rid of some of that freedom that you had in choosing your coordinate system, and you're choosing a particular gauge. That is, you're choosing a particular coordinate system. Okay, the coordinate system in which this equation is satisfied. Okay, partial mu of h prime mu nu is 0. Okay, so first I'll show that this can always be done. Okay, so let's write out this operator. So it's derivative with respect to y of h bar mu nu in the y coordinate system. Okay, this is the changed h bar mu nu in the y coordinate system. So we'll write this h bar mu nu in terms of h mu nu in the y coordinate system, which is just this. Okay, and now we'll switch to the x coordinate system. Okay, so we'll switch to the x coordinate system. So in the x coordinate system, okay, this h prime mu nu is related to h mu nu, okay, through this equation, through this dictionary, okay, which takes us from one coordinate system to another. So we'll plug in this dictionary for h mu nu, and we'll also have to plug in the dictionary for h, okay, and you can show that it transforms like this. Okay, that's easy to see, right? Basically, I just take the trace of this term. That's just partial mu psi, partial psi. Okay, and yeah, so I have minus half h eta mu nu times this. Okay, so each term, when I take the trace of it, will give me 2 partial alpha psi alpha. Okay, so when I say taking the trace, I always mean taking the trace with eta. Okay, taking the trace with eta. Okay, so if I say I'm taking the trace of this tensor, okay, and I really think of this as a tensor in Minkowski spacetime, then I multiply by eta mu nu. That's what I mean by taking the trace. Okay, which is really in terms of a matrix. If I have a tensor, I'm multiplying these two tensors together and then taking the trace. Okay, that's what, or these two matrices together and then taking the trace. All right. Okay, so now what we have is, yeah, so and the other important thing is this derivative with respect to y is the same as the derivative with respect to x till order lambda. Okay, because y and x are just related by an order lambda difference. Okay, so since I'm only working with something that is already order lambda, I will differentiate it only to leading order in lambda. Okay, and so what I get then is, so now I differentiated with respect to partial mu of x. Okay, this is all dependent on x. And now what I do is this term and this term can be combined into h bar mu nu. Okay, and now I write the derivatives acting on this, and then I write this term. So the derivatives acting on this give me minus box sine nu and minus partial mu sine nu. Partial mu psi mu, and this. Oh, sorry, did I mess up? No, this is right. Yeah, this last term gives me partial mu psi mu. Right, there's a minus half times minus 2, which is plus 1. This eta mu nu becomes partial nu when I multiply by this. Okay, so this acting on this, okay, gives me partial nu, sorry, lower partial nu, partial mu psi mu. Okay, so you see at the end of it, I have only one free index, which is nu, okay, which is the lower index. All right, the mu index is summed in every term. Okay, and I can now simplify this further. These two terms cancel against each other. Okay, so what I just get is partial mu h bar mu nu minus box psi nu. Okay, so what we wanted was we wanted to set this quantity to 0. Okay, by choosing our coordinate system appropriately, and we showed that this quantity is equal to this. Okay, so what that means is if we want to set this to 0, we just have to choose psi nu such that it satisfies this equation. Okay, you have to choose psi nu so that it satisfies this equation, and you transform your coordinates in such a way that you basically make this change. Okay, if I make this change, then it's guaranteed that in that coordinate system, this equation will be satisfied. Okay, that's the gauge freedom that you have. This equation can always be solved because supposing this is some non-zero quantity, then I'm just solving this sort of generalized Laplacian equation. Okay, and this always has a solution. Okay. Okay, so you can find a solution. This. Okay, so basically you can show that there's a Green's function for this, and so this is a linear equation sin u. Therefore, you can always find a solution to this. Okay, so anyway, the point was just to show that you can always make this choice by switching your coordinate system. So you're partly using your coordinate freedom to make this choice. Okay, you've not used all the coordinate freedom because you're solving a differential equation for psi. Okay, which means that I can always shift psi by a constant, and it would still satisfy the same differential equation. Okay, it would still satisfy the same differential equation. I mean, in fact, there's slightly more changes to psi you can make. So you're only partially choosing the coordinate system. You're restricting further your choice of coordinate systems by this choice. Okay, so this is called gauge choice. Okay, it's a gauge choice which is restricting your coordinate system. Okay, with this choice of coordinates, okay, or with this gauge choice, you now have a simplification. If you look at this was g mu nu. Okay, and now what we're saying is any derivative contracted with h mu nu, this kind of derivative is 0. Okay, in the coordinate systems that we're using. So what that means is this is a derivative acting on h. This is a derivative. Sorry, this is a derivative acting on h. This is a derivative acting on h. This is a derivative acting on h, but it's not contracted with indices of h. Okay, so this is non-zero, but everything else is 0 here by our gauge choice. Okay, so everything else is 0 inside. So g mu nu becomes really simple in this coordinate system. Okay, in this coordinate system or in this gauge choice, okay, g mu nu just is very, very simple. It's minus lambda by 2 times box h bar mu nu. Okay, so this is really nice, right? We've made a complete simplification of the Einstein tensor. Okay, this simplification was possible because there's so much freedom in the Einstein equations of changing your coordinate systems. We chose an appropriate coordinate system, okay, and also an appropriate variable. Instead of working with h, we work with h bar. Once we work with h bar and we choose these nice coordinate systems, in these nice coordinate systems, g mu nu takes this simple form. Okay, so you have to do a bit of work to get here, but it's possible to do this. Okay, that's the important point. Okay. So in this linearized approximation now, Einstein's equations are really simple. Okay, it's minus lambda by 2 box h bar mu nu is equal to 8 pi gn over c to the 4 times lambda t mu nu. We assume that t mu nu is first order. Okay, so therefore we are just solving this equation now. This is the first order Einstein's equation. Okay, the 0th order Einstein equation is trivially satisfied because eta mu nu satisfies in the absence of any stress energy tensor. Okay, so you're solving the full Einstein's equation. And t mu, so you're solving for g mu nu, and you expand g mu nu as eta mu nu plus h mu nu. Okay, and t mu nu you expand as vacuum plus order lambda. Okay, so if I take the 0th order pieces on both sides, that's trivially satisfied. The first order piece now, this is the equation that you have to solve. Okay, so the first order equation is really simple. It's now box acting on h bar mu nu. This is the wave operator, which is partial square, partial t square. In our metric convention, it's this partial square, partial x square, partial square, partial y square, plus partial square, partial z square. Okay, could not be any simpler, right? It's just a wave equation. Wave operator acting on h bar mu nu is equal to minus 16 pi gn over c to the 4 t mu nu. So it's a tensor equation. It's still a tensor equation. It's a tensor in the sense of special relativity now, right? This is a tensor in the sense that it's not a tensor of general relativity. G mu nu is a tensor in general relativity. This is a tensor in a Minkowski background. Okay, we'll show that. Okay, we'll show how H mu nu transforms. Okay, but it's a two-index object. Okay, that at the moment, let's just say this is a two-index object, and if we look at it, okay, we're just solving every component of this equation, every value of mu and nu. You're just solving a wave equation. Okay, a wave equation with some source, right? So it's a very simple set of equations in this linearized limit. Okay, so a couple of points here. The linearized equation is much easier to solve. It's much easier than solving that full nonlinear differential equation that we had, where the nonlinearity was on both sides of the equation. Okay, T mu nu also depended on the metric, if you remember when we did this, right? So it's highly nonlinear, that equation. It's very difficult to solve. In the linearized version is much simpler to solve. Okay, and the other thing is, because it's a linear equation, solutions can be superposed. Okay, which means if I have a small perturbation and I solve, okay, if I can now take two different small perturbations, superpose the solutions that I get. That's also a valid solution to the linearized equations. Okay, so as long as we are in the regime of validity of the source terms remaining small, that is, you're not adding up many sources to make a big source, right? You can still trust perturbation theory and superpose sources. Okay, that itself is very powerful. Okay, so what we'll do is we'll show that we'll solve for a particular T mu nu and show that it really gives you Newtonian gravity. Okay, if you remember in the very beginning of the class, the kind of equations we were guessing for gravity plus STR were really of this kind of form, right? It was some tensor, okay, times some second derivative operator is equal to stress energy tensor. That was the kind of guess that we had made. That guess is right, except it's only true in the linear approximation to general relativity. Okay, the full theory of general relativity you would never have seen if you did not guess the secret symmetry of general relativity, which is coordinate system invariance. So that is the big leap that Einstein made, right? Combining special relativity plus gravity is not hard. Combining special relativity with gravity, you would have got some equation like this. Okay, we had made a guess for some kind of equation like this. The big leap is to realize that the equivalence principle implies or suggests the coordinate invariance of the laws of physics. Okay, and when you do that, when you start with that as your starting principle, you get a highly non-trivial equation, okay, non-linear equation. But the equation is it's very tightly constrained. There are very few equations you can write down. Okay, and the Einstein tensor is equal to T mu nu is just the simplest second derivative order equation that you can write down. Okay, any questions here? Online? Yeah. So you have to be a bit louder because of the fans. Sorry, a little louder, please. Any other? Oh, here. Well, the reason is because this is the full T mu nu, because the leading order piece is anyway 0. Yeah, so that's what I said, right? In the beginning, I said I'll rewrite the stress energy tensor as explicitly I'm pulling out the T mu nu. So I'm really using this, where this is the full metric, and I'm writing it as lambda times T mu nu. Okay, I'm just making the lambda explicit. At the end of the calculation, anyway, I set lambda to 1. Okay. So at the end of the calculation, if I set lambda to 1, it doesn't matter. This equation is still the same. Right? Because I work to first order in lambda. I'm just keeping track of the fact that this is first order in lambda. The right hand side is first order in lambda. So in the small parameter, whatever that small parameter is, okay, this is the right equation to solve. Okay, now there are some interesting similarities between these linearized equations and the equations for electromagnetism. Okay, so the first is the gauge freedom itself. Okay, so h mu nu transforming to h mu nu minus partial mu sine nu plus partial nu sine nu. This is the gauge freedom of linearized gravity. Okay, the freedom to choose coordinate systems in linearized gravity. In electromagnetism, when you have the vector potential, are you familiar with this? Have you seen this vector potential before? A mu is a combination of the scalar potential plus the magnetic vector potential. Okay, and in general, these can depend on x and t. Okay, so instead of working with f mu nu, you can work with this vector potential. Okay, f mu nu is partial mu a nu minus partial mu a nu. Okay. Now, since f mu nu contains the physical, electric, and magnetic fields, you can always, since I'm acting with derivatives on a nu, you can show that I can transform a mu by something like a mu minus partial mu alpha, okay, where alpha is an arbitrary function. Then what would happen is this extra piece would cancel out inside f mu nu. Okay, it would not lead to any correction to the electric and magnetic fields. So I have a freedom to define a mu. Okay, by because without changing the electric and magnetic fields, I can always change my scalar potential and my vector potential. Okay, by this transformation. So you see that this gauge freedom is very similar looking. Okay, here I have a 1 index object and it can transform like this. Here I have a 2 index object, so it transforms in a more complicated way. Okay, but you see the similarity in the gauge freedom that you have. Okay. The second is the equation of motion that you find is this. Okay, you find box h bar mu nu is equal to t mu nu. Okay, so the wave operator acting on h bar mu nu is equal to some source. In electromagnetism, what you find is box a mu is equal to j mu. Okay, this turns out to be Maxwell's equations. Okay, is box a mu is equal to j mu, where j mu is the charge current for vector. And actually, these equations are only valid in a particular gauge. Okay, you make a particular gauge choice. So we made the gauge choice partial mu h bar mu nu is 0. Okay, in electromagnetism, you have to make the choice partial mu a mu is 0, and then the equations take this form. That is called Lorentz gauge. Okay, in electromagnetism. So you see that there's a lot of similarity between these linearized Einstein's equations and Maxwell's equations. But full general relativity is not the same as Maxwell's equations. It is completely a non-linear theory. It's only this linearized version that has some resemblance to electromagnetism. Okay. But in fact, we'll see that in this linearized approximation, you can actually have gravoelectric and gravomagnetic fields. Okay, so similar to how you have both electric and magnetic fields, okay, for a mu, okay, it's possible from h bar mu nu to define an analog of an electric field and an analog of a magnetic field. Okay, so gravoelectric field, gravomagnetic field. The gravoelectric field is what we conventionally think of as our standard gravitational potential. It's like the Coulomb force. Okay, but there's also an analog of the gravitational magnetic field. Okay, this is a new prediction of linearized Einstein's equation, which is necessary for compatibility even with special relativity. Right, just for compatibility with special relativity, you can't have Coulomb's law being the correct law, right? Because in a different reference frame, when the charge is moving, it produces a magnetic field also, right? Similarly here, you can't just have Newtonian gravitational attraction. When a mass is moving, it must produce an analog of a gravitational magnetic field. So we'll see that, okay, that you produce gravitational magnetic fields also. Okay, so this equation, okay, by the way, it turns out that just like this equation describes a spin 1 particle, okay, we've not shown that, you may not have seen that yet in your classes, okay, that this describes a spin 1 particle in Minkowski spacetime. This is the equation of motion for a spin 2 field in a Minkowski background. So sometimes you'll hear the statement that gravity describes a spin 2 theory. Okay, it's a spin 2 particle. What that strictly means is in a background of eta mu nu, so assuming no sources so that you're approximately in a Minkowski background, if I take small perturbations around that, then gravity is described by a spin 2 field. Okay, that's what we really mean. Okay, so this can be really thought of as a tensor field in Minkowski spacetime. Okay, so remember that, so we'll come to how h mu nu transforms, and I'll show you that really just the way we have defined how tensors transform in special relativity, h mu nu really transforms in that way, in the sense that h mu nu under Lorentz boost, okay, will transform to lambda mu prime, lambda nu prime, h bar mu prime. okay, under a Lorentz boost. Okay, so I'll show that this is the transformation rule that H bar obeys. So that really it behaves like a tensor field of special relativity. Okay, so in this linearized limit, okay, all the rules that I told you for special relativity in the special relativity course, or that you might have seen if you've taken the course elsewhere, right, for this dictionary of special relativity, that dictionary of special relativity really secretly emerges in the linearized limit of general relativity. Okay. Okay, any questions here? Otherwise, we'll move on to the next one. Any questions online?
We just made the prediction that there will be something called electromagnetic field and so on. So how do we understand that? I mean, for electromagnetic field, there's something like the Lorentz force now, which we can sort of say that okay, this is how it matter, and therefore we can sort of consider it, we can check whether there is some magnetic field in place. So there, how would we sort of consider some experiment to check this prediction?
We'll see that, but basically particles will experience these gravomagnetic forces, okay, and in principle it should be possible to test for them. The problem is that for typical gravitational fields, that we experience, this effect is far too weak to really realistically detect. That's why we have not detected it till now, and that's why it was not detected even before Einstein, postulated this law. It's a consequence of general relativity. It emerges as a law. Even if you had not guessed the full equations of general relativity, if you had only guessed the linearized version of general relativity, you would have found the existence of this gravomagnetic law. Okay. In fact, okay, I mean, it's interesting to speculate this. Maxwell's equations were known before special relativity was discovered. In fact, they led to the discovery of special relativity. But if somehow you came to the conclusion that special relativity is the right transformation law, you would have realized from the Coulomb law that the Coulomb law in some different inertial frame has to give rise to a different type of force on particles, and that force must correspond to some kind of magnetic field. So you would have discovered magnetic fields from the consistency of the Poisson equation for electric fields and the forces of the Coulomb forces between particles by using the dictionary of special relativity. So in this case, we had not discovered gravomagnetic fields first. We discovered special relativity first, right? So special relativity plus Newton's gravitational law implies gravomagnetic fields. Okay, and special relativity plus gravitational fields is anyway a special limit of GR, the full general theory. Okay, so let's just recap, okay, quickly where we were. So we worked in the linearized gravity approximation. We solve for g mu nu in some coordinate system where t mu nu is small. Okay, we are yet to define what we mean by small. Okay, but roughly speaking, at least for the metric, we know what we mean. We mean that in the coordinate system that we're working in, the components of h mu nu are small. Okay, compared to, because these are dimensionless quantities. H mu nu also has to be dimensionless, and the components of h mu nu are small compared to this 1, minus 1, minus 1, minus 1. So compared to these quantities are small. Okay, when we solve Einstein's equation, these quantities should emerge to be small. That's what we ultimately mean by smallness. Okay, now what does that physically mean? We don't yet know. Okay, that's what we're going to discuss, okay, today. Where we said that also the stress energy tensor is small. Whatever is causing this small perturbation to the metric is in some sense some small source. We've not clarified what that small means either. So we can either talk about the smallness of t, or we can talk about the smallness of eta. Whatever is the a source is small if it gives rise to a perturbation which is small. Okay, a change in the metric which is small. Okay. Okay, so in such a coordinate system, we expect the form of the solution to be this. Okay, where the components of h mu nu are small. Okay, so here I'm not writing the lambda explicitly. I'm just saying that h mu nu is some order lambda quantity, and we defined small h and small h bar. Okay, and we further restricted our gauge condition. And the point is that this does not fully fix the coordinate system. We still have what is called a residual gauge symmetry. We still have some freedom to choose our coordinates. In particular, and we found that with this gauge condition, Einstein's equation take this form. Box h bar mu nu is minus 16 pi gn over c to the 4 t mu nu. And what we're going to do now is we'll solve this for dust. Okay, that is a pressureless ideal fluid. Okay, so if a pressureless ideal fluid, if I set P to 0 for an ideal fluid, what we get is T mu nu is just this, where U mu and U nu are the velocity 4 vectors of the fluid element, okay, and which can vary from different space-time points to different space-time points. And the density of the fluid can also vary from one space-time point to another. So these rho and U mu are x mu dependent. And now what we're going to do is we're going to take a source which is slowly moving, okay. That is its speed, or the speed that goes into the 4 velocity, that is much, much less than the speed of light, okay. So we'll take a slowly moving source, okay. Now it is always possible, okay, to use the residual gauge freedom to go into a coordinate system in which at some particular space-time point the source is slowly moving, okay, because the source is spread out over many space-time points. Okay, this T mu nu, this fluid is present at many space-time points. The claim is that at one space-time point, okay, I can always change my coordinate system so that at this space-time point, okay, my source at this space-time point is slowly moving. Okay, that's the claim that I'm making. I'll show this rigorously. Okay. So let's suppose that at this space-time point in the coordinate system we're working in, U mu is large. Okay, so the velocity is large. Okay, there's a large velocity 4 vector. By that I mean this U mu at this particular point is something like c square root 1 minus u square by c square, u bar square root 1 minus u square by c square. What I mean is mod u is of the order of c, okay, in some coordinate system. I'm going to claim that I can use my residual gauge freedom, whatever freedom I have to choose my coordinate system, which is not fully fixed by this condition. The remaining freedom that I have, I can still use it in order to go to a coordinate system in which u mod u is less than c. Okay, but I can only do this at this point. Okay, I can only do this at this point. I can't guarantee this at other space-time points. So let's use the residual gauge freedom. So let's make a change of coordinates y. So we'll use a change of coordinates y mu is equal to lambda mu nu x nu, where lambda is an element of SO3 that is, it's some kind of boost matrix, okay, that we're familiar with in special relativity. Now, this is a coordinate transformation in general relativity, right? This is a general, I mean, you can make any general coordinate transformation. Y is a function of x, okay? But we've restricted the class of transformations that we could use. First of all, we insisted our transformations be small, okay? Second, we insisted that our transformations preserve this gauge condition, okay? That we have this gauge condition. Now, finally, okay. So under a general transformation, this 4 vector u, okay, should satisfy the tensor transformation law. It should be transformed as partial y mu, partial x nu, u nu. So if I switch to the x coordinate system to the y coordinate system, in general relativity, this is the dictionary, right, which takes me from the components of the old 4 vector to the new 4 vector. However, if this is my coordinate transformation, the partial y mu, partial x nu is just lambda mu nu. Okay, so what this is telling me, lambda mu nu is a constant here. Okay, lambda mu nu is a constant. So what this tells me is that the dictionary for general relativity in the case of this particular transformation is just the same as the dictionary that we had in special relativity. Okay, so the dictionary for how vectors transform in special relativity was that they transform with a lambda matrix. Okay, this is the law for general relativity under this special class of restricted coordinate transformations is exactly gives you the law of transformation in special relativity. Okay, and similarly you can show that h prime mu nu, okay, you can show that the full g mu nu, you know the transformation rule. Okay, the full g mu nu transforms with this tensor law. Okay, you can show that the linearized correction to this transforms with just the the dictionary for special relativity again. Okay, that again these derivatives give you lambdas. Okay, and what you get is effectively the transformation rule for h prime mu nu is as if it were a tensor in special relativity. Okay, so you can show that again, all these objects, right, when you're working in this linearized approximation, h alpha beta is like a tensor of special relativity. Okay, it transforms like a tensor in special relativity. Okay, and h bar mu nu also transforms like a tensor in special relativity, and h bar mu nu we said satisfies this gauge condition. Okay, that this is equal to 0. Um, and this gauge condition is also a condition that that transforms in different coordinate systems to this. Okay, so because this also transforms like a 4 vector. Okay, in special relativity. So this gauge condition is also satisfied in my new coordinate system. Okay, if I switch from x to y, the same gauge condition is satisfied. Okay, so that's what I meant by this condition does not fully fix your coordinate system. You can still make these Lorentz transformations in your coordinate system. Okay, and in my new coordinate system, this gauge condition will still be satisfied. Okay, so you still have some residual gauge freedom. I'm using this residual gauge freedom to go to a coordinate system in which the fluid element is moving with a small velocity. Okay, so we're switching to a coordinate system in which the fluid element, basically if that u is much less than 1, then it's approximately takes this form. Okay, it's approximately just 1, 0, 0. I'm just setting u to 0. Okay, if the speed ux, uy, uz is 0, then the forward velocity is just this. Okay, it's just 1, 0, 0, 0. Okay, c over square root 1 minus u squared by c squared, u is 1. So this is actually c, but let's say we're working units where c is 1. That's just this. All right.
So is it still a small coordinate transform if you transform a large 10 velocity to a small velocity?
Yeah, strictly speaking, it's not true. Okay. Yeah, strictly speaking, it's not true. But the other thing that we know about this transformation is that this coordinate transformation, even though it's a large coordinate transformation, it preserves eta mu nu. So the form of the perturbation is still preserved, right? Because it preserves eta mu nu, it doesn't affect the eta mu nu part at all. It just changes h mu nu components among themselves. Okay, so in that sense, it's still small in that it doesn't affect eta. The nonlinear part of the yeah, anything that changes you from eta mu nu to something that is not small, right? That is a problem, right? But anything that doesn't do this is okay. Okay. So we assume that this can only be done by coordinate transformations which are order lambda, but it can also be done for this class of transformations which preserve eta. Right? So this is a large set of large transformations which is still allowed.
So is this the right way to think about this, that we are introducing this h mu only after doing the transformation?
Yeah, you can say that. So we first make the choice of a frame, or we make a choice of this x goes to y using lambda, such that the fluid elements, the source terms, um, have small velocities, and in that frame, where the metric takes this form. Okay, and then we're making further. We can make small coordinate transformations which give this which preserve this gauge condition. Okay, but the point is that that initial choice does not is compatible with this gauge condition. Okay. Yeah, but we're going to make a stronger assumption. The stronger assumption is that all fluid elements are slowly moving. Okay, you can guarantee this at one point in space-time. Okay, by changing this, because this change of coordinates is a change of coordinates everywhere. This change of coordinates is a change of coordinates for every x you're changing to a y. You have only one choice that you can make. You can't make this choice everywhere. Otherwise, it becomes an x-dependent coordinate transformation. Lambda becomes a function of x, and then you have to differentiate lambda also in the coordinate transformation. Okay, we are making this choice where lambda mu nu is independent of x. And if you're making such a choice, then it's a very strong assumption that the fluid elements are all non-relativistic in this coordinate system. Okay, so we'll make that assumption. Basically, slowly moving source. Okay, this is an assumption of a slowly moving source in some coordinate system. Okay, so basically all the fluid elements are assumed to be slowly moving. In that case, this is true at all points, at all space-time points. U mu can be approximated in this form. If that is true, then we know that rho u mu u nu can be written as a matrix as just rho in the upper diagonal and everything else is 0. Okay. Okay, and we know that this must satisfy the continuity equation. Okay, this must satisfy the continuity equation. So if it satisfies the continuity equation is in the non-relativistic limit. I told you it's this fluid equation. Partial T rho plus del dot V is 0. We're in the limit where V is exactly 0. So that tells us that partial T rho is 0. Okay, that is the density itself is not changing. There is no flow to change the density in one region of space to another. And so the density in each region of space stays exactly constant. Okay, that's the assumption that we're making when we're saying that there's no flow, or that is V is much less than C, or V is 0. Okay, we're strictly in this limit where V is 0. So there's no flow. The density at every point, by the continuity equation, the density at every point stays constant. Okay. So rho is only a function of x, space. It's not a function of time. Okay, so it's only changing with space and not varying with time. And therefore, we expect that our perturbation is also only a function of x. Is not a function of time. Okay, so our linearized equations, which were this, now can be written as, okay. So first of all, we can separate out the 0,0 components and the non-0,0 components of this equation. So for mu nu non-0,0, the source is anyway 0, right? Because the source only appears in the 0,0 component. So so the right hand side is 0 for all of these, and it's non-zero only for the 0,0 component. Secondly, in that wave operator, I got rid of the partial square, partial t square, okay, because I assume there's no time dependence. Okay, so it's just a Laplacian. Okay, regular three-dimensional Laplacian acting on h bar 0,0 is minus 16 pi gn rho over c to the 4. Okay, so you see the equations are much simpler now. Right? Now our boundary conditions for this equation is, for the full g mu nu, we still assume g mu nu goes to eta mu nu at large xt. Okay, which means that we're assuming that h mu nu goes to 0 or h bar mu nu, the perturbations are dying out at large xt. Okay, this is an assumption that we're making. Okay, so for mu nu not equal to 0,0, h bar mu nu is equal to 0 is the unique solution. Okay, that is, if I look at this equation, my boundary conditions are that the field dies out, okay, at infinity. This will tell me that h bar mu nu is exactly 0. Okay, this equation tells me that h bar mu nu is exactly 0. Okay, this is just Coulomb's equation, right? Coulomb's equation in the limit that at the boundary there's no charge is that you just have 0 potential everywhere, right? That's what you get. So each component of this is like solving Coulomb's equation. Okay, so h bar mu nu is 0 everywhere. So the only non-trivial equation we have to solve is this one. Okay, for h bar 0,0. So for h bar 0,0, what we'll do is we'll redefine h bar 0,0 as minus 1/4 h bar 0,0 times c to the 4 is phi. Okay, we'll just call it phi. And we'll plug in, instead of h bar 0,0, we'll plug in phi over here. Okay. And something rather remarkable happens. Okay, you get the equation is now box square phi is 4 pi rho. Okay, so this is just a redefinition, but you might guess that this phi is just going to be the Newtonian gravitational potential. To show that this is the Newtonian gravitational potential, you have to ask what happens to a test particle moving in this metric. Okay, does it experience Coulomb's law? Okay, does it experience a force which is minus grad phi? Okay, you have to work out a test particle equation, which means you need to solve the geodesic equation. We have not shown that yet. We'll show that next. Okay, that a test particle moving in this background metric will have an equation of motion that looks like this. Okay, but already you can see that at least this part looks like Coulomb's law, right? You're solving, Poisson's equation, right? You're solving Poisson's equation for some kind of potential, okay, given some charge density. Okay, this is encouraging. It basically tells you if the sources are slowly moving, in fact, in the limit where the sources are static, okay, you get exactly Poisson's equation, okay, for the gravitational potential. Okay, in some particular coordinate system. Okay, in general relativity, if you work in a particular coordinate system, okay, where the perturbations are small, you get exactly Poisson's equation. Okay, this is encouraging. It tells you that you're getting Newton's gravitational laws in some limit of general relativity. Okay, now let's look at the metric. Okay, what happens to the metric? So the metric is there's only one non-zero component, which is this h bar 0, 0. Okay, so h mu nu, if you recall, was h bar mu nu minus half eta mu nu h bar. H bar itself was eta 0, 0, h bar 0, 0. H bar 0, sorry, it was actually eta mu nu, h bar mu nu. But all other components of h bar mu nu are 0. Only the 0, 0 component is non-zero. So eta 0, 0 is minus 1. H bar 0, 0 is this minus 4 phi by c to the 4. So h bar is just 4 phi over c to the 4. Okay. And so I can write out now what h mu nu is. H mu nu is, I can write out first h bar mu nu. H bar mu nu is only a non-zero 0, 0 component, which is non-zero. And then minus half eta mu nu times h bar. So minus half times this is minus 2 phi over c to the 4 times eta mu nu. So I have to add these two matrices together to get h mu nu. So h mu nu takes this form. Okay, so in terms of this function phi, okay, which we've anticipated is going to be the Newtonian gravitational potential, okay, which is only dependent on x because we assume the sources are slowly moving. H mu nu takes this form. So our full metric, which is eta mu nu plus h mu nu, I'm just going to drop the c because I'm not sure if I was consistent about putting the c. Okay, so c is equal to 1 in my notation. Oops. Okay, so this is the metric. Okay, so this is the metric. So we have to solve the geodesic equation to show that phi is really the gravitational potential, right? Because of course we can always redefine phi. How do I know it's phi? How do I know it's not 5 phi? How do I know it's not, why is this? Why should I interpret this phi as being the thing that causes a gravitational force on particles, right? For that we need to solve the geodesic equation. We need to see how a test particle moves in this metric. Okay, we'll do that later. Okay, we may not do that in this class. The important thing that I want to tell you is we will show that phi with this normalization, okay, is exactly going to be the Newtonian gravitational potential. And therefore, if I had chosen some other constant here, okay, by the fact that with this normalization, I get the right gravitational potential, that indeed tells me that this is Newton's constant, okay, Newton's gravitational constant. So the question of in Einstein's equations, why do we use 16 pi gn or 8 pi gn? Why do we use that Newton's constant? We do it so that we match Newton's laws, okay, with the exact constant over here, okay, in the limit of sources which are moving at low speed. So this choice of why Einstein's equations take the particular form that they had, we had two questions. One is, why do we use the Einstein tensor? Why not some other curvature quantity? That's because we want the stress energy tensor to be conserved. The stress energy tensor is automatically conserved because this is 0 is the Bianchi identity. Okay, so therefore the right hand side is automatically divergenceless. Okay, the second part was why this particular constant. Okay, the constant is chosen so that in the limit of slowly moving sources, the non-relativistic limit, okay, and plus an additional limit of weak perturbations, okay, you get Newton's gravitational laws. Okay, sorry, so we will take a few more minutes since we started late. Okay, so I'll just tell you, so we won't do the geodesic equation today. What we're going to do is I'm going to tell you what it means to have a small perturbation now. Okay, so what does it mean that these components of H are small? We can now understand that because we worked out what H is in terms of the Newtonian potential. Okay, so when we're saying the potential is small, when we're saying the perturbation is small, what we're saying is, if I restore the factors of c now, it turns out that there's a c over here. Okay, there's a 2 phi c square, and there's a 1 minus 2 phi over c square here. Okay, times c square dt square and all this. So what we mean by the perturbation is small is now really a statement that that phi is weak. That is, this 2 phi over c square. 2 phi over c square is a dimensionless quantity. Okay, so we're saying that the gravitational potential is small. Okay, so this gravitational potential is small. Okay, or the gravitational potential is much less than c square. So you have to show that gravitational potential has the same dimensions as c square. But let's go on. Okay, let's go on with this. Okay, so what does it mean for the gravitational potential to be weak? Okay, weak compared to what? Okay, so suppose we're solving Poisson's equation with a point source. Okay, so we have a mass and it's located at a point. Okay, so it's some delta cube r. So you're solving Poisson's equation with this rho, and we know that Poisson's equation gives you something like minus gm by r. Okay, in that case, so this is the potential due to a point mass, and in general we could have had a constant, but the constant is fixed by the fact that phi goes to 0. Okay, as at large x and large t. Okay, well, okay, let's just focus on large x here. Okay, I won't discuss the large t because we're assuming static sources. Okay, but really I have to assume that this source disappears at large times in the future and large times in the past. Okay, let's not worry about that subtlety. Okay, so let's take this and this. The point is that the perturbation should be small at large x and large t, because by assumption we get the Minkowski metric at large x. Okay, so the potential should die out at large x. It should go to 0 at large x. So that fixes this constant, okay, to be 0. Okay, so our reference level for the potential is fixed by our boundary condition for solving Einstein's equations. Okay, so there is a meaning to this absolute value of the potential at large x. Okay, we want to set it to 0. Okay, so this reference level is fixed by our boundary conditions. And what we need now, so the absolute potential has a meaning by itself. That's the first thing in general relativity, right? The absolute potential itself has a meaning because the reference level is set by the fact that asymptotically you want a Minkowski metric. Now, normally phi, you would always say I can always shift phi by a constant. It doesn't have a meaning. What we mean by phi is phi such that it satisfies the asymptotic boundary condition. Okay, so that phi dies out as x goes to 0. Now this phi needs to be small. Okay, that's what we mean by the weak field approximation. Okay, so Newtonian gravity emerges in the weak field approximation. So for a point mass, what it means is 2 gm divided by rc square. This is much less than 1. Okay, so I have to be looking at distances which are much larger than this constant, 2 gm by c square. Okay, so strictly speaking, my for a point source, my perturbation theory is not valid at all distances. Okay, it's only valid at these large distances. Okay, so for a point source, the gravitational field is strong when I get close to the point source. Okay, but as I get far enough from a point source, the gravitational field is weak. Okay, but this is not a problem for the entire formalism that we develop, because as I said, you can solve this on a patch. Okay, I can take a patch where I cut out a region near the source and I look far enough away from a point source. If I look far enough away from a point source with the boundary conditions that I have Minkowski spacetime, okay, in this coordinate patch, in this coordinate patch, that is everything where this field is weak. Okay, my entire formalism that I've done till now is absolutely valid. Okay, now what does it mean to be weak? Well, this is a constant. Okay, so this is a constant which I can define for any mass. Okay, given a mass, I know what this constant is. So this constant has dimensions of distance or length. It's called the Schwarzschild radius. Okay, so RS is 2 gm over c square. Okay, right now it doesn't have a physical meaning, but let's just say this is some constant which depends on mass. So if we take the mass to be the mass of the sun, which is 2 times 10 to the 30 kilograms, this distance turns out to be about 3 kilometers. Okay, so what this means is if you have a point mass which has the mass of the sun, okay, and if I am at a distance of 3 kilometers away from that point mass, okay, or much larger than 3 kilometers from that point mass, the gravitational field is weak. Okay, If I'm at a distance which is of the order of 3 kilometers, the gravitational field is strong. So I can always do perturbation theory as long as I am a distance r much greater than 3 kilometers away from this point mass. Okay, that's what. So that is the limit in which Newtonian gravity is valid. Okay, this is the weak field approximation. Okay, now the actual radius of the sun is 700,000 kilometers. It's not a point mass. Okay, it's not such a compact object that it's squeezed into a 3 kilometer radius. It's actually very spread out, which means that if I'm outside the sun, okay, by the shell theorem, I can treat it as a point mass in Newtonian gravity, and we can treat it as a point mass at the center. That approximation is valid in general relativity, because in general relativity, okay, outside this region, the Newtonian approximation is valid. You're very far from that point mass at the center. You're at least 700,000 kilometers away because you're outside of the sun. Okay, even inside the sun, if I look at any layer inside the sun, the gravity due to this layer, right, is always going to be weak. Okay, on any element outside it. Okay, because the sun is a very sparse object. It's not sufficiently dense. Okay. Similarly for the Earth, if I taken the Earth and I ask what is the mass of the Earth is about 1,000,000 times smaller than the sun. So the Schwarzschild radius is also 1,000,000 times smaller than the sun. It's about a few millimeters rather than kilometers. So if we are computing the gravity at the surface of the Earth, the radius of the Earth is 6,400 kilometers. So again, if I taken the entire Earth to be a point mass, okay, and if I'm within 3 millimeters of that point mass, strong gravity effects are important. But if I'm 6,400 kilometers away from that point mass, then the effect of strong gravity is not important. If the gravitational field is weak, my Newtonian gravitational laws are perfectly good approximation. So the thing is, Newtonian gravity works well in the limits where we expect it to work well. It works well for planets which are far from the sun. It works well for us on the surface of the Earth. Okay, so all of these limits, the gravitational field is actually very weak. Okay, so then the question is, when is gravity actually strong? When do you actually need general relativity? Okay, so when would gravitational effects would be strong? Well, if you have an ultra compact object of very high density. So if you took the mass of the sun and you somehow compressed it from the 700,000 kilometer radius object to a 3 kilometer radius object, okay, into something of a radius of a few kilometers. So imagine that you're now taking something which has a number density which is spread out over 700,000 kilometer cube, and you're now compressing this into 1/3 kilometer cube. Okay, look at how much you had to compress it, right? How much the density had to increase by a factor of 10 to the 6 cube. So by an increase in density by a factor of 10 to the 18, that's a ridiculous amount of increase in density. Okay, the sun is not very dense. Even at its center, it's not more dense than water. Like it's maybe 10 times more dense than water. Okay, it's not very dense. Okay, it's like maybe 10 grams per cc, maybe 100 grams per cc. But you're talking about something which has a density now of 10 to the 18 grams per centimeter cube. Okay, that's incredibly dense. Okay, so if you were compressed to something the size of a millimeter, let's say a kilometer, okay, or the entire Earth was compressed to the size of a millimeter cube volume, okay, and if you were near the boundary of this, you also have to be near the boundary. If you're not near, if you're very far from this, so if you compress the sun to within a few kilometers and you're very far from this, like if you're still 100,000 kilometers away, gravity is still weak. It's only when you come near to this. So first of all, you have to compress it. Then you have to come near enough to it that you can feel the strong gravity. Okay. Then non-perturbative general relativistic effects are important. Then Newtonian gravity is not a good approximation. Okay, so you have to be close to an ultra compact object with these ridiculously high densities for you to actually feel strong gravitational effects. Okay, such ultra compact objects are actually very difficult to form in nature. Okay, in nature, internal pressure prevents gravitational collapse. Why doesn't the Earth collapse to a small millimeter cube volume? It's because of pressure. Why doesn't the sun collapse? It's because of pressure. Okay, pressure prevents collapse. So getting something which is so dense is almost impossible. In fact, it was thought that it was never going to happen. Okay, matter resists squeezing. Okay, in the sun there is thermal pressure because nuclear fusion reactions create enough fusion that there's energy release. That energy release creates thermal energy. That thermal energy creates pressure, which resists matter from collapsing. Even in a star which is dead, which runs out of nuclear fuel, okay, where it can no longer sustain nuclear reactions, even in such, when you try to compress it, electrons obey the Pauli exclusion principle, so they don't like to be in the same state. So you have to put them into higher energy states. That creates tremendous pressure, okay, because you have to supply energy, okay, to go to higher energy states, and that creates pressure. That creates resistance to compression, and that creates what is called degeneracy pressure. So at the end stages of a life of a star, when it runs out of nuclear fuel, it can collapse under its self-gravity if there's no thermal pressure. But then degeneracy pressure can prevent further collapse. Okay, so Subramaniam Chandrasekhar actually showed, okay, in the 1930s on a boat ride to England, that electron degeneracy pressure will prevent stars from collapsing. Okay, and they will collapse to what are called white dwarfs. Okay, where the radius is still very large. A solar mass object will collapse to something which still has a radius of 7,000 kilometers. Still pretty large compared to that 3 kilometers. So where strong gravity effects will not be important. Okay, but what he also showed was rather remarkable, which is if the mass is greater than something called the Chandrasekhar limit, which is 1.4 solar masses, okay, then even electron degeneracy pressure will not be sufficient to prevent further collapse. The gravitational self-attraction will be so high that it will overcome even this degeneracy pressure. Electrons will still obey the Pauli exclusion principle. It's just, and they will still create large pressure. They'll have to go to higher and higher energy levels, but they will not be able to overcome the gravitational inward pull. Okay, even as they go to higher and higher energy levels. So, so this is called the Chandrasekhar limit, which is really famous because it really showed that it is possible. So the question was, what happens to such massive objects? Okay, now even degeneracy pressure cannot overcome the resistance to collapse. All right. Then it was okay. It was later shown that neutron degeneracy pressure can prevent collapse, but even neutron degeneracy pressure fails, and neutron degeneracy pressure can make you collapse to an object which is still a few kilometers wide. Okay, so this object is called a neutron star. For such objects, strong gravity effects are important. Okay, a neutron star is ultra compact. Okay, the entire mass of the sun is compressed into something of the order of tens of kilometers, maybe 10 kilometers. Okay, in radius. Okay, it's about 10 kilometers. Still larger than 3 kilometers, but not much larger. So strong gravity effects are important. But if you go to even higher masses, so something even greater than about 3 solar masses, neither neutron degeneracy pressure nor electron degeneracy pressure is sufficient to prevent collapse. Such a star, a very massive star which runs out of nuclear fuel, will eventually collapse to a point, okay, of ultra high density. Such an object is called a black hole. Okay, extremely high density. Okay, and basically what his calculation showed was that above a certain mass, okay, at that time they didn't know about neutron stars, but above a certain mass, at that time it was thought it was the Chandrasekhar mass, above a certain mass of 1.4 solar masses, you would collapse to something, but the question is, what is that something? Okay, it should be a point of very infinite density. And it was speculated these are black holes. Okay, it was a point of infinite density. So in fact, Chandrasekhar basically had a fight with Arthur Eddington, who was one of the persons who was very famous as an astronomer, who was instrumental in showing that Einstein's theory of general relativity was true. He showed this using the bending of light around the sun. Okay, he basically ridiculed Chandrasekhar's idea that the star can collapse to a point, and he said, no, there must be something which prevents collapse. It's just not possible. Okay, and Chandrasekhar in fact stopped working on this idea because he was so discouraged. Okay, after this argument. Okay, but later it was actually shown that there are solutions in general relativity which describe such points of infinite density, which are really in the strong gravity regime. You can't solve them in this linearized regime. Okay, so those solutions are black hole solutions. Okay, and we'll discuss those in some later classes. So if neither degeneracy pressure is sufficient to prevent collapse, you will end up with these black holes. For these black holes, if you're sufficiently close to the black hole, again, for a black hole, if you're far enough away, Newtonian gravity works perfectly well. You don't need to talk about Einstein's gravity. Far enough away, the law of gravity is still the same. It's just a compact object. But as I get close to the black hole, then that's when Newton's gravitational laws really break down, you really need the full power of non-linear Einstein's equations to understand what happens near a black hole. Okay, so that's what we're going to try to do. We're going to get an exact solution to Einstein's equations in the strong gravity limit. Okay, that is rather remarkable that someone came up with such a solution. Okay, the simplest solution that was known as the Schwarzschild solution, which we'll discuss in a later class. Okay, so I think we'll stop here. Any questions? I'm happy to take. So it does what? In the limit that the sources are absolutely static, it gives exactly Newton's laws. Okay. So basically, so there are two limits in which you get exactly Newton's laws. One is weak field. Okay, that is perturbations are small. Second is slowly moving sources. That is, the speeds are much less than the speed of light. Slowly moving sources and test particles. Okay, if the sources are moving with a speed comparable to the speed of light, or even a non-zero speed, you can show that they will create gravomagnetic fields which test particles will experience. Okay, so but it's still a weak field approximation. Mercury's orbit. Okay, so actually it's a strong gravity effect, which was the correction. It's still, so the Mercury's orbit is basically, now you have to be 3 kilometers from the sun, right? So roughly Mercury is not, let's say, order of 1,000,000 kilometers from the center of the sun. Okay, so the effects of strong gravity are suppressed by factors of 3 kilometers by 1,000,000 kilometers raised to some power. Okay, it's these effects that were tested, these strong gravity effects, which are still weak because you're far, but they're higher order corrections. Instead of order lambda, it's order lambda square type correction. Okay, that's what was observed for Mercury's orbit. Okay, so that's strictly outside of the linear approximation. Okay, it's not the gravomagnetic effect that's observed for Mercury. Mercury is still moving too slowly. The V by C of Mercury is too small, or the V by C of the sun is too small for you to observe this, the gravomagnetic effect on Mercury. The distance is what you're using. Yeah.
You said the source, you have a very small population, and you said that if we add infinite sources, then the population will be finite. But won't it be negligible because we are adding infinite sources for which the population is very small?
It's the question of the limits, right? N tends to infinity, lambda tends to 0. Which one wins? If n times lambda is finite, then it can be large. Right? I'm just adding up many lambdas. Yeah, and I have to add them all up at the same point, right? If it's spread out, right? I mean, a sun is a very spread out object, but at each point the density is sufficiently low, right? That I can trust this approximation. That is, the weak gravity is valid. Okay, thanks. We'll stop here and we'll resume on Monday.